Alright kiddos, hello. It is time for our last video. I apologize in advance if I am coughing because I am still sick. I know I was sick in the last video and I just can't get over it. So, but we have to make this video. This one's pretty straightforward and easy, I hope, because we've kind of already covered most of the information and the material earlier in the unit, but it's a good summary of everything that we've been doing. So let's get into 510 and 511, which we are putting together for our presentation, and we'll go forward. So we're going to talk about multi-step reaction profile diagrams, which sounds really scary, but it's not. The reaction energy diagram or reaction profile diagram are those energy diagrams where we have the reactants. Sorry, that's my other dog. We have the reactants, we have the products, and they have the hump between the two of them that looks something like this. And multi-step, meaning when we have the mechanisms with 2 steps or 3 steps or whichever, what they look like, and we've talked about this already. And then that's really 510, and 511 is a catalyst. There's not a lot that you have to do with a catalyst, but I'm just going to give you a little information about it. And actually, I'm giving you a little more than what AP wants you to know, but I just sort of feel so compelled to do so. All right. So let's get through this slide, which has a lot of words on it that are kind of scary, but then I'm going to show you what I'm talking about. So here we are. Reaction energy profiles, remember that's the graph, okay, can also be used to illustrate a multi-step reaction. So instead of having one big hump, remember I told you that behind that big hump there's it's like a curtain that covers it up, and you can look inside of it and see all the steps of the mechanism. So you can see if it's a 2-step, you'll have 2 humps. If it's a 3-step, you'll have 3 little humps. But when we draw for the entire reaction, we just draw 1. But actually there's a lot going on underneath that one giant hump in the middle, right? So as long as the energetics for each step are known, we can do that. Now, in a 2-step reaction, there'll be 2 transition states. In a 3-step mechanism, there'll be 3 transition states. Remember, the transition state's the top of the hill, 2 humps, right? Remember that the rate determining step is illustrated by the energy of the transition states, and it is going to be the largest activation energy. It might not be the highest hump, and it might not be the first hill, and we've already done this in a previous section. But remember, the largest difference from where it's starting and to the top of that peak of the hump, that's the activation energy. The largest distance is going to be the slowest step, which is your rate determining step. And then the intermediates can be identified as the valleys between the reactants and the product. Sorry, I'm trying to not cough. It's really loud. It's really loud, so I'm trying to not cough. All right, so the placement of intermediates is dependent on the energetics of each step. They could give you every bit of every step, the amount of energy from when you start into the end of each step, and actually have you draw it. They typically don't get that involved. They might ask you to sketch something, but it's usually not incredibly detailed. All right, so we have a couple questions over here on the left, but before we do that, let's look at this diagram. So remember that these are the reactants over here, and these are your products here, and it looks something like that, right? But then when we look behind the big hump, we see that this one has 2. So that means this is a 2-step reaction. And you're going to have to be able to label these, and it's not too terribly confusing, hopefully. It's a lot going on, but once you kind of sit and look at it, it's okay. So we have our reactants here, and we have our products down here like we discussed. We have the transition state at the top. This distance from where it started to the top of this peak is the activation energy for step number 1. This valley right here is an intermediate. And then this is where step number 2 starts, right? And the top of its peak. So this is the activation energy for step number 2. Now, let's look at our questions. It says, which step is the rate determining step? Well, what I'm looking for is this distance, which has the largest distance. I'm trying to cough again. Sorry, I'm trying to not cough. which is, we're looking for the one with the greatest distance between where it starts and the top of the hill. So for this one, step number 1. So which is the rate determining step? Step number 1 is the slow step. Why? Because it has the greatest distance from where it starts, which is here, to the top of the peak, which is the transition state. Also known as the activated complex. Please know that, because sometimes, depending on who writes your question, activated complex, AP will refer to that and this as the same thing. So just be aware. So that's number 1. And then the second question is the reaction endothermic or exothermic? So they're asking about for the whole reaction. So we're asking about the whole reaction. They're looking at just the reactants and the products. Well, products are lower in energy than the reactants, so this is an exothermic reaction. And this distance from the products to the reactants right here is your enthalpy, which is your energy. And it is negative because it's exothermic. Okay? All right. So now let's take a look at this one. And you have to label it. And you're like, oh my gosh, that's a lot to label. Just one thing at a time. Just do the easy stuff. Start with the easy. All right, right here's where I'm starting. Reactants. Here's where I end. Products. How many steps do you see? 2 steps, right? There's 2 steps. So there's 2 steps in this reaction. All right, let's see. What did we call the valley? What were the valleys called? Intermediates. All right, so now the top of this peak is called a transition state. And this is transition state for step number 1. And then I have the top of this peak, which is the transition state for step number 2. So we're slowly filling it in. We have this distance here, which is from where I'm starting to the top of the peak. And so that's my activation energy for step number 1. And then let's go find the one for the step number 2, since we're already on that. So we're starting here. So this distance, so we're starting here and we're going here. So this refers to the activation energy for step number 2. The distance from the reactants to the products, which is this line here, that's my enthalpy of reaction. I don't know the value because I don't have any numbers on my y-axis, but I do know that it's going to be negative. Why do I know that's going to be negative? Because overall this is an exothermic reaction. I know there's questions on the side when I haven't even looked at them yet. Now there's one that's blank. And let's look at that one for a second and see if we can figure out what that is. So we go from the reactants, we go up this hill, we hit the transition state, and we come down to this intermediate, and then we have more energy and we go up, and then we come down to the products. Great, but what in the heck is that? The distance from the top of this transition state down to the valley. In the forward reaction, it doesn't mean a whole lot of anything, but it is for the reverse reaction, right? So if this first step were at equilibrium for some reason, then it could turn around and go back. And so this is the new starting point here. And it's a starting point for the forward reaction. If we go, let me clear some of this out. This is the starting point for the forward reaction if we go that way. And it's the starting point for the reverse reaction if it goes back. So what would we call this point? This would be the activation energy for the reverse of step number 1. So that would be assuming if this, for this particular one, this step number 1 would be at equilibrium. All right, so which is the rate determining step? Well, for the rate determining step, I want to know which of these is the biggest line. For me, I think the second one definitely looks larger than the first one, so I'm going to say step number 2. Is step number 1 endothermic or exothermic? So they're asking just for step 1. They can ask you for the individual steps or for the overall. So if I'm just looking at step number 1, that means I'm going from here to this intermediate. Step number 1, the products or this intermediate step are higher than where I started. So the step number 1 is endothermic. All right, and then the last one is this reaction endothermic or exothermic overall. We've already addressed that it is exothermic. Sorry. I've addressed that it's exothermic, okay? All right, so that's pretty much it for 5.10. We're going to talk about catalysts. And I am going to go a little bit more quickly because a lot of this they're not going to ask you about, but I just kind of feel like I want to talk about it. So a catalyst is a material that's used to speed up the chemical reaction, but it's not used or consumed in the chemical reaction. It comes in and it comes back out, and it can be used over and over and over again normally. So they can happen, or they work in a couple of different ways. So they can alter the rate of the reaction by 1, changing the number of effective collisions that they have, or 2, by altering the chemical pathway into a different one that requires less energy in order to make the reaction move forward. Typically the ones that AP we're going to talk about are these two, but the third one we're just throwing it in there just for fun. So the first one is a homogeneous catalyst and a heterogeneous catalyst. They sound, the definitions, which I'll talk you through them, sound scary, but they're really, really, really very obvious when I explain it, okay? So just let's roll with it. Homogeneous catalyst is when your catalyst and your reactants are in the same phase. And a heterogeneous catalyst is when your catalyst and your reactants are in a different phase. So you got to think about what the heck the word phase means, which you should know. They're talking about solid, liquid, gas, that type of thing. So if your reactants are gaseous and your catalyst is gaseous, then that's a homogeneous catalyst because it's in the same phase as the reactants. If your reactants are gaseous and your catalyst is a solid, then they're in different phases, so that's a heterogeneous catalyst. It's that simple. Don't overcomplicate it. That's all it means. And then an enzymatic catalyst, so sometimes we'll talk about enzymes as the most common catalyst that you would know coming into AP Chem because you've had biology. And we sometimes discuss enzymes. So an enzymatic catalyst, it's going to speed up the reaction by binding. So what it does is it comes in and binds with one of the reactants that is happening to do whatever it's trying to do. And it creates a more favorable orientation for the reaction to take place, okay? And so it just creates a better looking surface in order for the reaction to happen, and then the enzyme will go off and continue doing it over and over and over again. So an example of a homogeneous catalyst is, let's say we have the decomposition of KClO3 and the catalyst is MnO2. All right, so this overall reaction is endothermic. Why? Because my products are higher in energy than my reactants. Hold on one second. Sorry. My crippled dog just took herself downstairs. Is she okay? Mm-hmm. Okay, she's okay. Anyway, back to this. She just couldn't wait for me to finish. And so KClO3 will decompose into KCl and O2. So that's what's going to happen. And it will happen. But you can throw in some MnO2 and it's going to make it happen more quickly. So you have the black line, which represents the uncatalyzed reaction. And then once you throw in the MnO2, it's represented by the yellow line, and it just lowers that activation energy. So there's several things that can cause it to lower the activation energy, but that's really not what AP gets into. Just know that the catalyst lowers the activation energy. That's what you need to know. They might ask you, is it homogeneous, is it heterogeneous? Well, in this particular case, this was a homogeneous catalyst. So pay attention to that. In this case, they're both solids. Sorry, I didn't mean to cross it out. I was trying to underline it. The KClO3 is a solid. The MnO2 is a solid. And that means they're in the same phase. So it's a homogeneous catalyst. I wanted to talk to you real quick about how this is written. In an overall chemical reaction, not showing the steps of the mechanism, but the overall, MnO2 is written usually above or could be directly below the arrow or the yield sign, indicating that it is a catalyst that's used to speed up the reaction, but it's not actually in the chemical reaction. Now you also notice there's the triangle on top. And so the triangle, we call that delta. And you guys know that, well, try that again. And you guys know that delta means change. But in this case, when we write it over an arrow like this in a chemical reaction, it also means heat. So they had to add heat in order for this decomposition to occur. And so just so you know, that's what that symbol means. It is not a requirement to know that for AP chemistry. However, it's there, so I wanted you to not be confused by what the heck that meant. Okay, so let's take a look at this. This is the hydrogenation of ethene. This sounds crazy, but look, this is ethene right here, the C2H4. Hydrogenation means I'm adding hydrogen to it, which we know is a molecule that's H2. Now we also know a lot about H2. It's very, very small, right? And so when H2 is, when we have two hydrogens that are bonded together, it's not super easy to break them apart. It requires a good amount of energy. So it requires a lot in order for these two to react on their own in order to create, in this particular case, ethane, which is what they're trying to make. So what they do is if you throw in this nickel, which is just a solid piece of metal, if you throw in nickel, what happens is the hydrogen, the H2, will run into the nickel, the solid metal. And when that happens, it breaks the high H2 apart. And so that makes this hydrogen more available to bond with the ethene. And it doesn't require anywhere near as much energy when H, just this monatomic H, reacts with this guy. It's very low energy, as opposed to this H2, because you've got to put in a lot of energy to split them up. So this hydrogen, the monatomic hydrogen, will bond with the ethene, and then you'll slowly start to get to the next step. It's one at a time. And then you'll get to the ethane, which is the goal. And so this is heterogeneous. Why? Because hydrogen is a gas and ethene is a gas, and then solid metal it's just a metal. And so it's solid. So the nickel is acting as the catalyst, but he's in the opposite phase or a different phase from the reactant, so it's heterogeneous. Now here's another one that pops up a lot. You'll hear people talk about, and you might have heard of it before, but a catalytic converter in a car. So in a combustion engine, you have a lot of really nasty byproducts at the end. So you have carbon monoxide, nitrogen dioxide. There's tons of things that are really you don't want being spit out into the environment. And so the creation of something called a catalytic converter, which is also a heterogeneous catalyst, and catalytic meaning catalyst. And how it works is it's usually this honeycomb shaped metal that it could be platinum is used a lot, palladium, rhodium. Those are different metals that they tend to use a lot because they will help with the reaction between these nasty molecules. And so what happens is the nasty molecules will come in, they'll go through this grid of the platinum or whatever it is, and it will cause these reactions to occur. And then what we get on the backside is carbon dioxide, nitrogen gas, and water vapor. And we know that carbon dioxide also has its other issues that it causes for our environment, but it's better than the carbon monoxide. So, you know, it's still better. But the point is, these things coming in are gases. The metal that's in this catalytic converter is not actually binding or doing anything. It's just providing a surface to increase the reactions between those reactants, so they turn into something that's a little bit better for our environment. And the catalyst sorry the platinum and such is a solid, so that makes it a heterogeneous catalyst, and that's it. Okay, so this is from 5.10. So they want us to sketch a reaction diagram for a 3-step mechanism that is exothermic overall. All right, so I'm homing in on this. So first steps first, I'm going to start with the basics, which is my reactants and my products. And if they didn't want just, they just wanted an exothermic reaction, you would, done, right? That'd be simple. But of course, they want us to show the 3 steps. So I'm starting here and I'm ending here. And they didn't give me any other information about the steps. If they wanted to say step 1 was endothermic and step 2 was exothermic or whatever, you would have to make sure that you did that. But they didn't tell me, so I'm going to do what I want. So I'm going to do this. I don't know, I just feel like doing this. Do whatever you feel like doing. They don't tell you. All right, so the overall, this is exothermic. Let's take a look at what I did here. This is exo, it's 3 steps. Hopefully you see that step number 2 is my slow step and my rate determining step, because there's this distance, and that distance. And this is the biggest activation energy. And they didn't ask us for anything else. That was it. That's all I had to do. Easy peasy. All right, so then this next one, and this is from 5.11, so this is the end of it. So the rate of decomposition for hydrogen peroxide can be increased by adding a homogeneous catalyst. The reaction mechanism occurs in 2 steps as shown below. So they want us to write the overall reaction, identify the catalyst, and identify the intermediates. Okay, perfect. So let's take a look. We have hydrogen peroxide. We know that the iodides are going to cancel out. And since it initially shows up on the reactant side, that's going to make it my catalyst. And I see this hypoiodite here. And initially shows up on the product side, so that makes it my intermediate. And I have H2O and O2. All right, so the overall chemical reaction, I have 2 hydrogen peroxides, decomposes, and I get 2 waters and an oxygen gas. Now note, the state of matter of the hydrogen peroxide is aqueous, and the state of matter of the catalyst, which was the iodide ion, is also aqueous, meaning it's a homogeneous catalyst. Now, if we were to write this overall reaction, this is all you have to do in AP. And I don't want you doing anything above what you have to do. Don't do it. I know some of you are tempted because you just want to be so smart, but don't. But technically, when you get to big boy, big girl chemistry in college, you have your iodide that would go in either on top of or right underneath that arrow in the chemical equation, okay? Don't do that here. Don't do it for AP. Just write the overall reaction, don't include it. Identify it this way. But that's it. All right? I know you heard me, and you know who you are, and you know who I'm talking to. Don't do extra. All right, so that's it. We're done. I'm done coughing in your ear, and I'm sorry. I will try and get this downloaded and then uploaded into our website ASAP. All right, bye guys.